Hello, welcome to another problem session. So we're gonna do the third problem. First two problems are in the previous videos from the 2024 JEE advanced paper. So here is the question a little bit expanded, and if you like my approach of doing problems, you may also enjoy using this website, my website for physics. So let's see. So here is a really interesting problem. Okay, so on a horizontal table, okay, so it's not a vertical thing. So horizontal table, you have a ring. On that ring, you fix a bead with some kind of positive charge Q, and then you place another bead over here anywhere, but this will be a stable place exactly opposite end. So the force on this bead, the electric force on this bead will be in that way, and bead will push against the ring, and the ring will push against the bead, uh, and those two forces together with this force will balance the force. But if you displace the bead a little bit over here, now this is electric force, and it will start to oscillate about because it's not equilibrium anymore. So it's going to be oscillating back and forth uh, around the equilibrium, and both being positive, so that's the highest repulsion, right? Uh, so uh, the question is, what is the frequency of this? It's a very interesting question. Okay, so when things are oscillating like that, you always kind of look for equations like x, some variable x double dot equals minus some positive constant omega square x. So if you can somehow get this to come out, maybe x coordinate of this guy. So this is xy. So if this is called x and this is y, then over here the y x is so in this case will be y double dot and y, because x will be close to 0 and y will be very small, y small, making the origin maybe rather than over there, you make the origin over here and make this y as y-axis. So x will be 0. If you put origin over here, then x will be the kind of radius, regardless. Or if you put origin over here for the sake of setting of the problem, then x will be like a 2 times the radius. 0, depending on where it puts the origin. But the y-axis, the y-coordinate will be just very small. So if you can somehow figure out equation of motion of this particle and you manipulate it so that you get some constant, so from there omega is the angular frequency, and that's what the question is trying to do. And you can actually do it another way. You can say, well, it's kind of like a pendulum, and I'm going to see if I can do this angle theta. So another way is to do the theta double dot equal minus omega square theta. So this is another way you could figure out what the omega square will be like. But I find this one is much more direct, okay? And let me clean this up and try to do this implementation. And although I see a lot of people do this implementation, I I think this is a little more work than necessary in my view. In pendulum, it turns out this is easier, but over here, because the force is much more easily, you can write force in the x component of the force and the y component of the force. All right, so let me work that out for you and clean it up, and then I'll be presenting that. Okay, so I'm going to choose origin over here. Just doesn't matter where you use, but choose here. Okay. If you want to do it, maybe you can choose origin here, and maybe you can try to do origin here just for practice. All right. With this origin, electric field is pointed that way, and so you can write down electric field as some k. K is 1 over 4 pi epsilon naught. Okay. K q square, and then you are going to have a direction vector from here, which is going to be, it's in this direction, so it's going to be xi hat plus yj hat, and then the distance 3/2, right? So you're going to be x square plus y square 3/2. Okay. So now I'm going to replace this with 2r and replace this with 2r, and we're going to say y is much less than r. Okay. And I'm not going to worry about the x component, so I'm just looking at f e y component. So just look at that. Okay, q square y over 2r plus y square 3/2. Let's pull 2r out. So you have a kq square over 2r square 2r square 3/2. You pull that out, and over here you have a y over 1 plus y over 2r square. Okay, and this is 3/2. We can this do nothing with this. We just pull it over here, and so we can just say pull that over there. 1, and this is y, and this whole thing is like 1 over 1 plus epsilon some small quantity to the power 3/2, which is equals to, if you expand it, was 1 minus 3 over 2 epsilon plus like that. Epsilon is small, you can just keep up to there. But you can see that this is going to be, let me just show it, k q square y over 2r. Now this tool gets this half and becomes a cube, and this is going to be 1 plus 1 plus 1 minus 3/2 y square over 2r square plus like that. Now this is very small compared to that. We've already assumed that, so we can just forget this and forget all the higher order terms, and this is just 1. So indeed is proportional to y, and it will be a restorative force. There will be force that will be by the ring, which will restore this, and that's the force that will cause the so we'll see that this mass times acceleration y, and we can say the acceleration y is proportional to the y is proportional to the y, which means this quantity divided by m will be omega square. Omega square will be k q square over 2r cube m. Now just k is 1 over 4 pi epsilon naught. So this is going to be q square over this 8 times 4 is 32 pi epsilon naught r cube m, and answer is B. Okay, so this is a strategy of doing this kind of problems. Okay, maybe you can try to do it in the other variables I mentioned earlier. We can try to do it in like a theta variable over here. So it would be like a pendulum. You can redraw this to be more familiar. Like you can put this point over here and that point over there, and so you're looking for the angle theta, so you're looking for that component, you know, the restoring force in the theta direction, and so that would be another way of doing it. Okay, so I'm going to stop this and try to do another problem today. Okay.